Morning, nerds. Just a minute ago, I went ahead and I did an example. I redid this example, but I thought that what we should do is maybe make up another one. That way you could see another one happen and just see how it works. You don't have to have it written down, but I feel like this skill is going to be the hardest one for most people on your upcoming test, which I'm going ahead and tell you now, this skill is on that test. So I wanted to make up an example and just go through it just so you could see it happen again. That way you could see that the patterns don't change. I'm going to make up a new function, and then I'm going to find its inverse. Again, you don't have to have this written down. I don't know, I'm just kind of making this stuff up as I go. There. Okay, that's a new function. And I'm telling you, it does have an inverse, and we can find it. The first step for finding an inverse function is switching x and y. So this is a y, it's going to become an x. These two x's will become a y. Our job is to isolate the y value, get y all alone. And just like before, like I said, in that example, I have the y's in the top and the bottom of the fraction, and that causes us a problem. So multiply both sides by the denominator. On the right side, they will cancel. And on the left side, you will distribute the x to the -3 and to the y. There. Now we are trying to get y by itself. So what we want to do is we want to group our like terms. We want all of the things with y's on one side and all the things without y's on the other side. It really doesn't matter which side I bring the y's to. So tell you what, I'll bring my y's to the left this time. And things that are not y's will go to the right. So here I'm going to have xy minus 2y. These are gone. These are gone. I'll have 3x minus 1. Yeah, I could have written -1 plus 3x, but that's weird. So there you go. And just like before, we're trying to isolate y. The only way to get the y alone is to undistribute it from here. Notice that it is a GCF and it can be factored out. And then lastly, cancel that multiplication with the division. And this is an inverse, so we wouldn't leave it as y equals. We would write it as f inverse of x equals. And there you have it. So notice, you're probably going to have to multiply by denominators to get rid of the fractions, then distribute, then group your like terms, then factor. Yes, sir?
I got -3x plus 1 over 2 minus x.
You got the exact same thing that I got. Because if you factor a -1 out of the top, you'll get that. And if you factor a -1 out of the bottom, this 2 becomes negative, this x turns positive. And the -1s will cancel out. So your answer's not wrong. It's just written slightly different. What do you think? Could we pull that off? Yes, ma'am. What's up, Charlie?
Like on the test, would you accept either of those answers?
They are the same answer, but because a question like this would be on the multiple choice part of a test, you would need to know that if you didn't see your answer somewhere, that maybe it's just that you needed to factor out -1s. So have to watch out for that. Okay? Because I will be honest with you, every multiple choice question, I'd say, well, 95% of them have an option that says none of these. And if you got this and then selected none of these, it would be wrong because that is the same answer. So we just need to be on the lookout for order of things. Basically, I wouldn't leave this in this order. I would have immediately made this -x plus 2, and then I thought, wait a minute, I got negatives on the front, on the top and the bottom, and then I would have gone from there. Yes.
How did you get x minus 2 out of xy minus 2?
From this right here, we used it as a GCF. If you remember back in algebra, if you'd done stuff like this, and so I asked you to factor that, you'd see that both of those numbers are divisible by 2. So you could undistribute the 2 like that.
Oh.
But I was seeing that both these things are quote-unquote divisible by y. So I treated y as the GCF and just pulled it to the front. Yes, sir.
So, I've noticed that the denominator is x minus its coefficient on the numerator.
Okay.
The original equation, and the numerator for the second equation is 3x. So, swapping out the coefficient.
Kinda. The problem, no, it's not coincidental. I mean, even the same basic thing is happening here. It's just that the coefficient here was 1. They both had a coefficient of 1. So then rather than looking for, are there patterns that exist? Yes. But honestly, I think it would be more work to try to memorize the pattern and figure out where things are going to go than it is to just do the algebra. But it's not a coincidence. It's not a coincidence. And the reason why it's not a coincidence is because when you find an inverse function, you are literally finding a set of instructions that does all the same math the original one did, but in reverse order. So if you took a number like x equals 5, let's just say you had to plug that in. Here you'd multiply, then subtract. Here you'd subtract. And the very last thing you would do is divide. Well, here, it's going to be all the same operations, but they're in the reverse order. So if you took that number 5 and you plugged it in, now it's multiply, subtract, subtract, divide, but the numbers switched places. So no, it's not a coincidence, and there is a pattern, and it's because you're literally doing all the same math in the reverse order to quote unquote undo what f of x did. Like an inverse operation, this was positive, so I subtracted. It's the same math in an opposite order. Yep. Okay. The reflection principle says that if two relations are inverses, then a coordinate a comma b on the original becomes b comma a on the original. On the inverse. There we go. I can talk. Basically, your x's and your y's switch places. Like right here. Switch x and y. If you can recall from geometry, switching x and y is the same as reflecting over the line y equals x. If you don't recall that from geometry, no big deal. But that's what it is. Two graphs are inverses of each other if they are reflections over the line y equals x. Every x becomes a y, every y becomes an x. So here, we can sketch the inverse of this function. Before I do though, we know this is a function because it passes the vertical line test. Does it pass the horizontal line test? Yes, it does. It also passes the horizontal line test. A little bit sketchy on that was a 3-day weekend. Remember, horizontal line test. This fails the horizontal line test, which means its inverse is not a function. See, this one passed the vertical line test and the horizontal line test, which made it 1-to-1. This graph is a function because it passes the vertical line test. This graph does pass the horizontal line test, meaning a horizontal line does not hit it more than once. That means its inverse is also a function, which means it is 1-to-1. So I don't even have to sketch the inverse to see if it's 1-to-1. I could just see it because this passes both tests. Let's go ahead and get that inverse sketched though. 2 ways of doing it. One is by taking the coordinates, writing them down in a point tree, and switching x and y. So I would be looking for the pretty points. Those 3 are pretty, meaning if I had a grid, they would hit perfect grid points. So what is that? -1, 0, 0, 1, 1, 2. This is on the original function f of x. And for the inverse function, we will switch x and y. And then plot those points and connect our dots. 0, -1, 1, 0, 2, 1. Now, I'm not a very good artist, so what I'm going to do is I'm going to go ahead and put the line y equals x on there because it'll help me see how to reflect and how to connect these dots, because, I mean, honestly, they're in a straight line. I could connect it with a straight line and be wrong, and I don't want that to happen. So what I'm going to do is 0, 0, 1, 1, 2, 2. That's the line y equals x. And I'm going to put the line y equals x on here as a dotted line because I am going to reflect over that line. And I'm going to leave my paper sideways too. Dang, I always mess this curve up. But you could see it. It's pretty close. I can never get it flat enough. But anyway, there it is, the inverse function in blue. And another reason why I wanted to throw y equals x on there is to show you that if your original graph intersects the line y equals x, your inverse function will also go through that exact same spot. And Sebastian, you asked me a question a minute ago, and my answer to you was it's the same mathematics, just in reverse order, basically canceling each other like inverse operations, right? Okay. The inverse composition rule basically says what I just repeated to Sebastian. It says, if f and g are 1-to-1 and are inverse functions, then f of g of x, composing them in this order, will result in x. Almost as if the letters f and g cancel each other because they're inverses. G of f of x, composing in this order, will also give you x because, almost as if g and f cancel each other, they are inverse functions. I mean, everybody's cool with inverse operations canceling things, right? Like if I wrote the square root of 4 squared, what would the answer be? It'd just be 4, because the inverse operations cancel each other. Well, if you treat your functions as operations, and I tell you f and g are inverses, then they cancel each other and leave behind a lonely x. But that only works if they're 1-to-1. Cool? Okay. We use this composition rule to verify that two functions are true inverses of one another. And I have to use the word true inverses of one another because there are times when the composition in one direction works and the composition in the other direction does not work. So we've been tasked with showing algebraically that these two things are inverse functions. That means we have to compose them in both directions. And both directions have better equal x at the end. I'll do f of x in blue. I'll do g of x in red. So that means I'm going to take my function f, which will be my blue function, and everywhere there was an x, I'm going to have a set of parentheses filled with red g of x. There was an x here, and I fill it with red g of x, cube root of x minus 1. And just like you saw me do here, cube roots and cubes, third roots and third powers, cancel each other. That leaves behind x minus 1 plus 1, which is just x. So it works in that direction. Yay! Yay! Not like we were surprised, because we were told to verify that it's a true statement. So we already knew their inverses, so it had better worked. Now I'm going to do it in the other direction. So I'll take red g of x, and everywhere it had an x, I'll have a set of parentheses. And I'll fill those parentheses with blue, f of x. This happens to be one of those times where the parentheses didn't do anything. And that's okay. So because they did nothing, feel free to not write them. Because the plus 1 minus 1 is going to cancel, we're going to be left with the cube root of x to the third, which we know is x. So since composing in either direction left us with x at the end, we could show that f will cancel g and g will cancel f. Pretty neat, huh? Back when I was an Algebra 2 regular teacher, I used to hold my students to very high standards. I mean, very high standards. And after teaching this lesson, and we had practice and stuff like that, this was their test. This is one of the questions on their test. Number 8. Now, they had never dealt with anything to the 5th power yet, or even 5th roots yet. But I specifically told them, these two things are inverse functions. Find g of f of 2. And then I gave them lots of space underneath it. Anybody think they know what the answer is? Kate, what's the answer? It's 2. Because I specifically said that g and f are inverse functions. You don't do any math. Literally, these two letters just cancel each other, and the answer is 2. The students that understood that concept, like 2 of them, just wrote 2 and did no work. Everybody else attempted to take this function, plug it into this, and stick a number in there, oh, by the way, with no calculator, and would get lost in the algebra and give up. Or you could just know that they're inverse functions, so g and f cancel each other, and the answer is 2. Yes, Ashley? I don't know. The students used to say to me, well, then why'd you give me all that space? And I go, oh, I mean, I had to give you enough space to, I gotta be, okay, so it's kind of a dark joke, but it comes from a saying. You ever heard the saying, given just enough rope to hang yourself with? And I used to tell them, I'd be like, well, I had to give you enough space in case you decided to use that rope. But, the answer was just 2. No work to be shown. You ready for the extra credit question on that test? I said f and g are inverses, p and q are inverses. That means this g and this f cancel each other, this p and this q cancel each other. The question actually is it just simplifies to f of q of 1. Oops. So literally all I had to do is plug 1 into q and get 3, and then take 3 and plug it into this and get 7, and you were done. Takes that much work. But most people just saw this and went and left it blank. But why? If you understand inverse functions, you understand that they cancel each other, and there's no reason to leave it blank. Huh? But they don't, but again, well, you guys might not know this about me yet. Have any of you been my students before? Math students before. None of you. I will often give questions that look remarkably difficult as extra credit, but if you know what you're doing, they're very easy. Now, unfortunately, Sarasota County has adopted a testing platform wherein it is impossible for me to have an extra credit question on a test. Yeah, I know, right? Isn't that ridiculous? Either their programmers are idiots and can't program, so couldn't figure out how to do it, or they're idiots and had no idea that teachers might want to have extra credit questions on tests. Either way, they're idiots. So that's what's up with that one. Now I'm not done with this old test. We'll come back to it in a moment. Here we have the function f of x equals the square root of x plus 3. This is its graph. Before we even read any directions, because these directions are about inverses, this is a function. It passes the vertical line test. Does it pass the horizontal line test? Yes, it does. What that tells us is that it has an inverse, and the inverse is a function. Because this passes the horizontal line test and the vertical line test, this is 1-to-1. It has an inverse, and the inverse is a function. Let's go ahead and sketch that inverse real fast. There's a pretty point, hits at a nice grid spot. There's a pretty point that hits at a nice grid spot. And the last one that's pretty is right there. Now, do you have to write out the point tree? The XY point tree? No. I'm only doing it for really good note taking. There. So if I want my F inverse point tree, I switch X and Y. Zero comma negative 3, 1 comma negative 2, and 2 comma 1. Now, once again, I'm not the world's best artist. So to make sure that I do a really good job of reflecting this thing, I'm going to put the line y equals x on here as a dotted line. So it goes through 1, 1, 2, 2, 3, 3, so on and so forth. Like that. That means there'll also be a point right there, because anytime a graph intersects the line y equals x, its inverse will also go through the exact same point, like I showed you on the previous example. And I'm going to do my best here to something like that. Not too bad. Now the actual directions for this question were to find f inverse of x, its equation. Algebraically, that means switch x and y and get y alone. Okay? That's not new. Let's go ahead and do it. I haven't used enough purple and green today, so I'm going to use those two colors. I'm going to switch this x and this y. X equals square root of y plus 3. Trying to get y by itself, what's the first thing I need to do? I have to square both sides because I'm trying to cancel a square root. Those two structures cancel each other, leaving me with x squared equals y plus 3. You get y by itself now with a single step of algebra. You subtract 3 from both sides, and you get y equals x squared minus 3, but we're not going to leave it as y equals, because this is the inverse function. We're going to write f inverse of x equals x squared minus 3. And now that you know that is the equation of the inverse, you should have a problem with its graph. What kind of graph is y equals x squared minus 3? It's a quadratic, a parabola. Look at your blue graph. It's only half. It's only half. Now, Jack W. said something about the domain. It can't what? Well, if this is half, we have half a domain, don't we? But the question is why? I'll tell you why. Because in order for a graph to be a function and to be 1-to-1, its inverse, which would also be a function and would be 1-to-1, you need for every x there's exactly one y, and for every y there's exactly one x. You need to be able to switch all the x's with all the y's. So for this black graph, it had no y values less than y equals 0. And when that statement becomes x's. So you say, what are the y values that exist for this black graph? Oh, y is greater than or equal to 0. Look at my blue graph. Only exists for x is greater than or equal to 0. Why? Because this thing's domain is the inverse's range. This thing's range is the inverse's domain. All the x's and the y's have switched places. That means the domain and range has switched places. So when you are dealing with square root graphs and their inverses, which are technically quadratics, your job is to cut the quadratic in half. This one, its domain is x is greater than or equal to 0. So anytime you're dealing with a square root graph and a quadratic, your job is to cut the domain in half for the quadratic. But you have to be careful. You have to choose the correct half. And you want to be able to do that without graphing. So the question becomes, how would I have known that this was the domain of this thing's inverse without graphing? The point of the graph was for you to believe that this had to be done. But how could we pull this off without graphing? It works like this. Because of transformations, which we will review after we do the next test, but it's because of transformations. So there's the general form of all square root equations. And that number on the front, it could be positive or it could be negative. Square root graphs are supposed to point up and to the right. Do you remember way back in section 1.2, 12 basic functions? Or was that 1.3? It's 1.3. There's the parent square root graph. It points up and to the right. So if this number is positive, this graph points up. If this number is negative, this graph points down. From where? From that number. Up from that number or down from that number. Whatever that number is. This is how you get the range of the square root graph. So why would I want the range of the square root graph? Because the domain and range switch places. So the domain of the inverse function, the one that has to be restricted, is the range of the square root graph. So this is how you get the range of the square root graph, which is the domain of the parabola. The restricted domain of the parabola, I should say. So one last example, just to really drive it home. Actually, even better, my old test. It says, restrict the domain. I've given a function and its inverse, and then said use the symbols to properly restrict. You can't see the word restrict, it's over there though. See, restrict the domain of f inverse. So I gave them this square root graph, and then I said restrict the domain of this using these symbols. Well, in reality, we needed to be looking at this thing. It has a negative on the front, so it points down from this number. See, that stuff on the inside didn't matter. this thing's range is less than or equal to, goes down from this number. Of course, that question I asked in inequality notation. Like that. What that means is F inverse, the domain was that. You just write X instead of Y. Yes, Adi?
What if the stuff on the inside of the square root equal to 0?
Well, the stuff on the inside of the square root, there's an X in there. So it won't equal to 0 unless you have the very specific X value. So you don't have to worry about that. Because the square root graph, in and of its nature, already has a restricted domain. And that's one of the reasons why we need to restrict its inverse. Because this is a restricted graph, its inverse is going to be restricted in some way as well. Now, we think of this thing having a restricted domain, but in all reality, as a restricted range as well because of the way square roots are calculated. It's pretty neat though, huh? Again, I left them a lot of space, but all you had to know was points down from -1. And so you just wrote less than or equal to -1. Very easy. Okay. Thank you, nerds. Appreciate you.